Hello students, welcome. So in previous lecture or in last offline lecture, we discussed about halides of phosphorus. In this lecture, we are going to discuss about oxoacids of phosphorus. Now oxoacids are compound which contains OH group and acidic characteristics, and H plus will be released from OH group. We already discussed about it, how it is possible. So phosphorus forms number of oxoacids. The important oxoacids of phosphorus with their formulas, method of preparation and the presence of some characteristics bond in their structures are given in following table. So first one is hypophosphorus acid. So as the name suggests, hypo prefix and OUS suffix, it indicates lowest possible oxidation state. So it has +1 oxidation state. It contains one POH bond, two PH bond and one P double bond O bond. Now in usual cases, POH bond or our element with OH group attachment is compulsory because it is in definition of oxoacids. So number of OH bonds simply represents the basicity of acid, and in the meaning of basicity is if acid can release one H plus, then it is considered as monobasic. If it can release two H plus like H2SO4, then it is considered as dibasic, because after the release of H plus, whatever the left is, it is in basic nature. Simple example, if we check the reaction of H2SO4 after the release of first H plus, if it releases H plus, then you will get HSO4 minus. Okay, so this is first conjugate base. Okay, so this is first conjugate base of H2SO4. It can release one more H plus and you will get SO4 2 minus. So this is conjugate base number 2. So because it can produce two different basic compounds, it is known as dibasic. Or in simple manner, we can say that because it releases 2H plus, we can call it dibasic. So number of OH bonds in oxoacids usually indicates basicity of given acid. That means our first compound will be monobasic. Second is orthophosphorus acid, so H3PO3. It has +3 oxidation state which contains two POH bond, one PH and one P double bond O bond. Now usually ortho and pyro type of words or prefixes will be used if compound has different type of spatial orientation of attached group. In the attached group we have OH, H and O in this case. So different type of attachments can lead us to different type of compounds. If you notice the oxidation state of second and third compounds, then they are +3. So that's why because of +3 OUS prefixes are used. Lower oxidation than that means +1, it contains hypo prefix with OUS suffix. So ortho and pyro in these two cases, they simply represents the arrangement of different type of groups attached with it. So it is a different type of situation. It is not based on oxidation state. Ortho and pyro, it is like D and L type or optical activity type process. Different type of arrangements in space lead us to different type of name of compound. So both of them contains +3 oxidation state. This is a dimeric molecule, that means it contains two different monomeric unit attached with each other, which can give us a large molecule. So number of OH bonds, they are similar in both of the cases. It has two OH bond. But first compound contains one PH and one P double bond O. Second compound contains two PH and two P double bond O bonds. Now usually P block element shows alternate oxidation state. That means +1, then +3, then +5, then +7, or +2, +4, +6. They do not show sequential oxidation state like D block elements. D block elements can show sequential oxidation state, that means +1, +2, +3, etc. But P block usually shows alternate oxidation state, but in their some compounds they even show continuous oxidation states or sequential oxidation state. As we can see in this case, hypophosphoric compound of phosphorus, which has +4 oxidation state. Now this is not regular oxidation state, that's why hypo prefix is used with IC suffix, which is not regular naming. But if compound shows different oxidation state, then we have to add more names in it, and that's why hypo and IC suffix is used. This compound contains 4 POH bond, so it can release 4H plus. It has 2 P double bond O bonds and 1 PP bond. Then we have orthophosphoric acid, which contains plus 5 oxidation state. It contains 3 POH bonds, so it is tribasic, 1 P double bond O bond. Then we have pyrophosphoric acid. It also contains similar oxidation state, which is plus 5. It contains 4 POH, 2 P double bond O and 1 POP bond. And last one is metaphosphoric compound, and it only exists in polymeric form. That means we have HPO3 monomers attached with each other in a long chain, which lead us to metaphosphoric acid. In metaphosphoric acid, we also have plus 5 oxidation state. It has 3 POH, 3 P double bond O and 3 POP bonds. So as we can see, all of the last 3 examples have similar type of oxidation state. That's why only IC suffixes are used. But because of different type of arrangements of the reactive groups attached with the central atom, they share 3 different type of names: ortho, pyro and meta. Okay, so this naming scheme actually based on attachments and their spatial orientations. If different type of orientations are there, then ortho, pyro and meta will be used. The composition of the oxoacids are interrelated in terms of loss or gain of H2O molecules or oxygen atoms. The structures of some important oxoacids are given in next page. In oxoacids, phosphorus is tetrahedrally surrounded by other atoms, so that means it should have sp3 hybridization. All of these acids contain at least 1 P double bond O bonds and 1 POH bonds. The oxoacids in which phosphorus has lower oxidation state, less than plus 5, contains in addition P double bond O and POH bonds, either PP bond, as for example H4P2O6, or PH bond in H3PO2, but not both. At least one will be present. These acids in plus 3 oxidation state of phosphorus tend to disproportionate to higher and lower oxidation states. That means product will have higher oxidation state than the reactant and lower oxidation state than the reactant. That means you will get at least 2 different type of products which contains one higher oxidation state than the reactant, one lower oxidation state than the reactant. For example, orthophosphorus acid on heating disproportionate to give orthophosphoric acid and phosphine. So you will get H3PO3 on heating, it gives H3PO4 and PH3. And let's check the oxidation state of each phosphorus present here. So total 3 hydrogen will give us plus 3, total 3 oxygens will give us minus 6. So that means 1 P should give us plus 3 oxidation state. So total it will be neutral. On the other hand, in product side we have 3 hydrogens, so that means plus 3, 4 oxygens will give us minus 8. So here phosphorus should be in plus 5 oxidation state. So as we can see, higher than the reactant. And in next example we have PH3. So in this case phosphorus shows minus 3 oxidation state because hydrogen is electropositive than phosphorus. So hydrogen will show plus 3, total 3 hydrogens will provide plus 3, which is lower than the reactant. So you will get 2 different type of products from the given reactant. One has higher oxidation state, other has lower oxidation state. And here different type of structures of different type of oxoacids of phosphorus are mentioned. The acid which contains pH bond have stronger reducing properties, thus the hypophosphorus acid is good reducing agent as it contains 2 pH bonds and reduces, for example, AgNO3 to metallic silver. AgNO3 plus 2H2O with H3PO4, it leads Ag, that means reduced silver. These pH bonds are not ionizable to give H plus and do not play any role in basicity. Reason is difference of electronegativity between phosphorus and hydrogen is very less. So if hydrogen is removed, hydrogen attached with phosphorus, if it is removed, it will get its electron with it. it will take its electron with it, so no H plus will be released. Either it will release in form of hydrogen atom or it won't release at all. That means you cannot get H plus when hydrogen is attached with phosphorus because of very less electronegativity difference. So then only option available to get H plus is from OH group. So only those H atoms which are attached with oxygen in POH form are ionizable and cause the basicity. Thus H3PO3 and H3PO4 are dibasic and tribasic respectively, as the structure of H3PO3 has 2 POH and H3PO4 has 3 POH bonds. So as we can see in these structures, we can simply say the basicity, we can simply find the basicity based on number of OH. If you compare three examples given here, orthophosphoric acid, orthophosphorus acid and hypophosphorus acid, then you will notice all of them contains 3 hydrogens, but they have different type of basicity or number of H plus released from them are different. First example contains total 3 OH groups, so that means it can release 3 H plus, and that's why it is tribasic. On the second case, orthophosphorus acid, it has 2 OH groups, so that means it can release only 2 H plus, that's why it is dibasic. And last example, it contains only 1 OH group, so it can release only 1 H plus, and that's why it is monobasic, like HCl. So these hydrogens, those are attached with directly phosphorus. Because of very less electronegativity, they cannot be released in form of H plus. That's why only option left is hydrogen attached with oxygen. From next lecture we will start the discussion about group 16 elements.